Any equation that relates temperature, pressure, and specific volume of a substance is called an equation of state, and often I denote that as EOS. So you may be familiar with the ideal gas equation of state, which for the most time in this course we'll write as P lowercase v times RT. You may also be familiar from chemistry, P capital V is equal to, say, nRT, or in this case, R needs a bar over it. Or equivalently, this is PV is equal to mRT. Do keep in mind, if you divide through by mass, you get the top equation. Let's see, what else we could do? We could write this as P V bar over R bar T, and do everything on a molar basis, where V bar is equal to the volume over the molecular weight. Now let's denote this as a more rigid M. So that is volume over molecular weight. Now, we can apply this ideal gas model to many different gases, including air. And R is different for each gas. And is determined by so this is the universal gas constant over the molecular weight here, and at least in SI units, R typically has units of kilojoules per kilogram times Kelvin. Do note that this is the same units as specific heat. So the value of the universal gas constant, Ru, you may remember from chemistry, is 8.314 kilojoules per kilomole Kelvin. And in English units, it is 1.98588, a value that I do not have memorized, and that's BTUs per pound mole times degree Rankine. For air, and this is worth committing to memory because you will use it so often in this course, for air, R is equal to 0.287 kilojoules per kilogram Kelvin, and you'll maybe also see that as 287 joules per kilogram Kelvin. Okay. In fact, water vapor can be treated as an ideal gas below 10 kilopascals. We rarely get to deal with water at such a low pressure, but in any case, that shows you the applicability of the ideal gas equation of state. Now, real gases do deviate from the ideal gas equation of state, and deviation from this equation of state can be captured by the compressibility factor. We denote that as a capital Z, or Z if you're English. So Z is equal to PV over RT, And really what it is, it's a ratio of the actual specific volume of a gas, V subscript actual, over the ideal specific volume of a gas. For an ideal gas, we would expect our actual volume is equal to the ideal volume, so Z equals 1. And when Z equals 1, you will see that we end up with the ideal gas equation of state. For real gases, Z can be equal to 1, it can be greater than 1, and it can be less than 1. Okay, now quantitative similarity in gas behavior can be achieved by normalizing pressure and temperature by the critical pressure and temperature. We call these reduced pressures and reduced temperatures. So let me define those here and write what I just said. So this will be P subscript R, so this will be the pressure of my fluid divided by the critical pressure of my fluid, and then the reduced temperature, T subscript R, will of course be T over TC. So yeah, so what these allow us to do is kind of quantitatively compare the behavior of different gases by normalizing those gases by their critical pressures and temperatures. Now if you look in your book, you will see a chart called the generalized compressibility chart that lists the values of Z for different gases across a range of pressures. So that will allow you to get a very nice pictorial view of how much a gas deviates from ideal behavior over a range of different temperatures. And because the ideal gas equation of state is very much ideal and doesn't really capture the behavior of any particular gas very well over a broad range of temperatures and pressures, there have been other attempts to create equations of state that are more broadly applicable. One of those popular equations of state is called the van der Waals equation of state. The van der Waals equation of state looks something like this. P for pressure plus little a over V squared, where V is, again, specific volume. A stands, or it represents intermolecular interaction. Van der Waals recognize that molecules interact with each other. They attract and repel one another. And this is multiplied by V minus B, where B represents the volume occupied by individual molecules. And that, of course, equals RT, as before, compared to an ideal gas equation of state. So do note that if A and B go to 0, if we say that there's no intermolecular interaction between gas molecules, and gas molecules in and of themselves have absolutely no volume, then this equation becomes the ideal gas equation of state. Another equation that you might run across is the Beatty-Bridgman equation of state. Make sure I spell Mr. Bridgman's name right. So here we have pressure equals the universal gas constant times temperature over V bar squared, and that's equal to 1 minus a constant over V bar T cubed times V bar plus another constant B minus another constant A over V bar squared. And then finally, I mean, there are many equations of state. We don't have time to talk about them all. But finally, I want to mention the virial equation of state. And virial is not named after a person. And what it says is that pressure is equal to RT over V plus a series of what are called virial terms, and what is on top of each virial term is a virial constant, which is a function of temperature. So here we have A, B, C, etc., etc. And these are determined experimentally and theoretically from statistical measurements. So what this equation allows you to do is add more and more terms, and the more terms that you add to the virial equation of state, the more accurately you can represent the behavior of a gas, just by adding more virial terms. But do note that without any of the virial terms, we are again at the ideal gas equation of state.